Hello everyone, welcome to this presentation. Thank you Professor for giving me this opportunity to present my today's topics, and thanks all Class Plus for attending this session. So this is Omar Faruk from Advanced Sensor and Energy Research Lab, and Professor J. Young Park is my academic supervisor. In this presentation I would like to talk about the second chapter of review of MMIC technology, that is indium gallium phosphide gallium arsenide HBT foundry. So here is my outline. So it's going like introduction first, then active device modeling, VBIC model and extraction of the various element, then passive device, then design rule. So first introduction, foundry service. So in this foundry service process, customer use the multi-project wafer application, which describes sharing of the wafer, and before fabrication of the company request a NDA, that means non-disclosure agreement submission. Signing of this agreement means that the customer can never uh, abuse its content. The regular shuttle run in is then verified, and then following payment of the mask manufacturing cost, the circuit design are submitted passing through the DRC, that means design rule check. Then following that, the mask is fabricated through PCM, and both the customer and the company uh, know if the process goes wrong. So then secondly, indium gallium phosphide gallium arsenide heterojunction bipolar transistor is a process is a semiconductor fabrication technique used to manufacture high performance bipolar transistor. The HBT process can be separated into two parts. One part is connected with the transistor aspect, and the other includes the rest of the MMIC and its backside. So types of process and their merits. Three types of process are involved in this process. One is high power process, secondly high linearity process, and thirdly high speed process. And all are practical application and characterized as tabulated here. You can see from this table. Then active device. The active device must have the characteristics of amplification and non-linearity. Additionally, it requires a DC bias such as TR and triode and diode. In this section, only HBT are mentioned. And here you can see a cross-sectional view of indium gallium phosphide gallium arsenide heterojunction bipolar transistor. So the 3 to 4 HBTs have a heterostructure that takes advantage of its superior transport properties that include electron mobility and velocity. And the substrate of gallium arsenide material with a high resistivity, because of the heterostructure junction, which possesses a band gap difference between the emitter and bias, and this system has higher emitter injection efficiency and higher current gain than homogeneous one. And to increase the electron mobility, a very high base dropping concentration and a very thin base thickness are achieved by epitaxial growth. So that means epitaxial growth is used here to increase the electron mobility. And the key feature of indium gallium phosphide gallium arsenide HBT device. So some are listed here. First of all, this is high frequency operation. So this can make them suitable for use in radio frequency and microwave circuit. So low noise figure. So these characteristics this feature making them ideal for application requiring minimum signal degradation, such as in low noise amplifier and used in communication system. Then high gain, this feature allowing for efficient signal amplification in RF and microwave circuit. Then high breakdown voltage, ensuring reliable operation even under high power condition. Low power consumption, making them energy efficient option for battery powered device and portable electronics. Temperature stability is essential for applications subjected to various environmental conditions. So, and indication flexibility can be integrated into complex integrated circuit. And finally, process compatibility. And now the HBT device are shown here in micrograph of indium gallium phosphide gallium arsenide HBT, and here also the HBT epitaxial structure is shown here. And in this 2.1 figure, you can see the indium gallium lace, and this the purpose of this indium gallium emitter lace is to prevent surface recombination current. So this lace performs as a significant role in the reduction of noise, and there is important relationship between the noise and the emitter to bias spacing in the indium gallium phosphide gallium arsenide HBT. And modeling of the device. So in this section we will discuss about extraction of the parameter of the VBIC model. First of all, parasitic, intrinsic, DC and AC parameter are required to achieve a perfect model. So additionally, AC measurement is performed using a vector network analyzer, and then modeling software is used, including the integrated circuit characterization analysis program. And the modeling measurement setup is shown in this figure. You can see in the right figure. And the HBT device characteristics are tabulated here. You can just look on time and then finish. And then VBIC model. The VBIC model was developed as an industry standard replacement for PSPICE PON, that is SGP model, and VBIC model was intended to improve the deficiency that exists in SGP model. So the basic configuration is shown in this circuit, that is figure 2.12. The VBIC model is 4-terminal model and comprised of base, emitter, collector, and a substrate. And the current flowing into this terminal are IB, IE, IC, and IS. So the other node of the VBIC are the extrinsic base, parasitic base, intrinsic emitter, intrinsic collector, and extrinsic collector. The model include an intrinsic BJT, that means NPN transistor, and parasitic BJT, that is PN p-type model with a partial SGP model. Now extraction of the parasitic elements. So parasitic, first of all, parasitic capacitance. The HBT T model, a small signal equivalent circuit, is shown in this here, and here you can see a parasitic capacitance in the input and output to the ground, CP on and CP on respectively. The CP on and this parasitic capacitance is extracted by open patterning. Second is parasitic inductance, and this is extracted by short patterning. You can see from these two figure, and the right figure is a photograph of short pattern. From this you can observe the parasitic inductance. And thirdly, overlap capacitance. So between base collector, the base collector overlap capacitance is explained in this part, and the capacitive coupling due to the geometric overlapping between the base and the collector in this HBT can give rise to charge feed through, and the exact value of the base collector overlap capacitance is determined by measuring the S parameter of HBT with 0 volt applied to the base emitter junction. and therefore no current flows, and a varied reverse bias is applied across the base collector. And then now extraction of the intrinsic element. So intrinsic element composed of resistance and thermal resistance. So resistance is about the average resistance in the flat frequency range, and the thermal resistance is the defined as the rise in junction temperature above the temperature of any reference point. And the extraction of DC model parameter, gamma plot, Gummel plot, and IV characteristics curve. An extraction of AC model parameter on is junction capacitance, another is transition time parameter. Passive device. So in MMIC design, passive devices are used for impedance matching, DC biasing, phase shifting, filtering, and many other functions. So a wide range of distributed transmission line, MIM, that is metal insulator, metal capacitor, spiral inductor, and resistor via hole, and pads are shown. First, transmission line. So the microstrip is a flat type strip of conductive material separated from a single ground plane by a dielectric substrate such as gallium arsenide, and that does not possess same shielding advantage at strip line. That means it has some disadvantage, but it has higher radiation loss, accessible for trimming in a circuit. Dielectric constant must be replaced with effective dielectric constant, and this microstrip line is useful for interconnecting the component of microwave circuit. Here the physical parameter of line metal and the physical parameter of substrate are tabulated here just for information. Now MIM capacitor. So MIM capacitor is most popular capacitor because high capacitance per unit area. So that means a smaller and less costly circuit are possible, and DC block matching section and biasing circuitry are widely utilizing this component. So feature of MIM capacitor here. This is thin film capacitor, and it composed of two metal plate that is separated by a dielectric layer. And typically dielectric material layer is overlapped the first metal, and the second metal has a smaller area than the lower metal layer. The area of the air bridge post determine the capacitance value, and the thickness of the dielectric layer is fixed in this open boundary surface, and the capacitance is approximately linearly proportional to the air bridge via model. Then a spiral conductor. The spiral conductor is a two-port multi-turn planar inductor. You can see from here, and a turn in the spiral inductor is the length of a complete 360-degree revolution, and the width and spacing of the strip in the spiral inductor are uniform throughout. Due to the high Q factor, the spiral inductor has become popular, and it is shown in figure 2.33, and the inductance value of the service provided by the K company, and they provide two types of square spiral inductor that is shown in right to figure, that is entirely air gap bridge type and the straight type. Then resistor. The resistor in MMIC can use the dropped semiconductor material layer of deposited thin film resistive layer. In this case, the material of resistor is nickel chromium thin film, and it can this resistor offer improved linearity and lower temperature coefficient, and the sheet resistance of about 50 ohm per square can be produced, which is convenient for circuit designer. And this is via hole. The backs. Oh, this is mistake, not register. This is via hole. The backside of the vial are used to connect the device of RF circuit on the front side, and the metallized back inside for grounding and thermal dissipation. And substrate via hole is available for 95 micrometer thickness. Vial may be modeled in RF device as a single port from the front pipette, and the configuration and physical parameter of vial is given in this figure. You can see. Then layout design rule. So relatively few design equations are used in the description of passive device because they are highly process dependent. And for particular MMIC, four general considerations are considered, and that is the maximum stepping tile size, the transistor orientation, the prototype of MPW 16 max layout, you can see from here, and GDS2 stream file format and standard cell. uh, Design rule type. So there are six type of simple layout design rule that is described in this table. This is our final slide that is related to design rule check. So design rule check is important for the engineer to check all or part of the design to confirm whether it meets the manufacturing specification. So there are two types of DRS. One is quick check, another is custom check. So quick check is like a quick check is pertain to minimum width and spacing, so basic design are required. And in case of custom check, it carried out according to a pre-written set of rules, and this DRC procedure is given in this figure. First define or select a design rule, then run the design and defined or selected rule, then load the result, view any error that were found. So this is all for today's presentation. Thank you all for your attention.